Welcome to Programming in Modern C++. We are in week 11 and I am going to start discussing module 51. In the last week, we have started talking about the modern part of C++, covering C++ 11 primarily, and there are several general features that we have covered which are listed here. The important general feature that we have discussed is the difference between copying and moving, particularly what is the difference between L value and R value, and what is move semantics, and how the move in C++ can take advantage of the move semantics to have better performance. We have seen std::: move function also in the standard library. We will continue on that in the current module. We will try to understand how R value reference works as a universal reference under template type deduction, and the problem that arises due to forwarding of parameters known as forwarding problem that happens in the template type deduction. We try to learn how universal reference and std::: forward function can work for perfect forwarding of parameters. We will understand the implementation of std::: forward and understand how move is an optimization of the copy, what is the solution that C++ 11 is actually giving us. So, this is the outline which will be available on the left. So, starting with discussion on universal reference, let me quickly specifically recap a few key concepts that we did in the last module. One is of reference collapsing, that is we observed that when we use the template in terms of C++, often we will have multiple references coming for a particular type. So, in C++ 03, there was one reference collapsing rule, so that you have T reference and another reference, then this will be collapsed to a single reference. So, reference to reference does not make a sense, it is reference to the original. So, this is what is not only in this kind of a template, when we try to do an invocation and binding using this function f, then T becomes int ampersand, and therefore, we have in total we have the function having a type T ampersand ampersand, which is collapsed to the T ampersand. In C++ 11, we have R value references. So, there are 4 possibilities, 4 possible combinations, and we learned the collapsing rule that reference collapsing involving any L value reference will always collapse to L value reference, and reference collapsing when it involves only R value reference, it will collapse to R value reference. So, this is the only rule where R value and R value will collapse to R value, otherwise it will always be L value. So, we need to keep this in mind, and this will be typically used here. Now, if we look at the T ampersand ampersand parameter deduction in templates, particularly if I have an R value reference parameter in the template, then we know that this will go through the template type deduction. And in terms of template type deduction, what it does, when it actually a parameter is passed, whether to this template f, this definition of the template f, if I pass if I call it with f x, where x is an L value, then actually an L value will be passed. So, this is a L value reference, and you have the R value reference. So, due to collapsing this will become an L value reference. The same thing will happen if I pass an R value reference. So, I will have an R value reference and that will collapse to R value reference only. Similar thing, this is for plain old data type, the same thing will happen for the user defined type. So, we get a very specific feature that if the template parameter is an R value reference, then when L value is passed to that in place of that parameter, then it will become an L value reference. If an R value is passed to that parameter, then it will become a non-reference or a R value reference, right. So, this is a very nice property of the R value reference template parameter, which is kind of referred to often as a magical reference type. So, that for R value arguments it binds with R values, for L value arguments it binds with L values. So, what we get if we summarize, that if I have a plain function with R value reference, then the calls to this function will bind only with R value references, that is non-constant R values. Right? Whereas, if we have a universal reference, what is universal reference? If we have the R value reference in the context of a template parameter, then because of this property of reference collapsing, if I pass an L value for this template, then it will behave like an L value reference. If I pass an R value, then it will behave like an R value reference. So, it is kind of takes two different contexts. So, and that is the reason this is called a universal reference, that is, it is adapting itself to the type of argument, whether it is an L value argument or it is an R value argument. According to that, the binding will become appropriately different. In this connection, we also note that the auto feature that we had studied earlier, that auto we mentioned that it follows the type deduction, which is of templates type deduction. So, if I have auto ampersand ampersand, that is auto of R value reference type, then those will also behave like the universal reference. So, here we have a L value generator, a function call which will give a value, and here we have a variable which is an L value. So, if I initialize the auto variable v1 with calc val, which is an R value, right. So, the type deduced by the auto ampersand ampersand going by the template type deduction will be int ampersand ampersand. That is, it will deduce a R value reference type, whereas if I initialize it with a L value, then it will deduce a L value reference due to reference collapsing, because auto follows the type deduction of the templates. So, auto ampersand ampersand also behaves like the universal reference. But if we try to do something equivalent using say Deckel type, we have seen Deckel type, I can take Deckel type of each of these, and then I in style of the auto, if I try to put 2 ampersands, it will not behave like a universal reference, because Deckel type, as you know, always extracts the actual type devoid of the references. It gets the actual type. So, whether it is an L value parameter or it is an whether it is an R value parameter or it is an L value parameter, the type deduced by Deckel type will be just the int. Therefore, if I use 2 ampersand after this, it will both become R value reference. It will not behave like a universal reference. So, this is the key behavior that is important to understand for the universal references. Universal and R value references are can be compared very easily, both use the same ampersand ampersand syntax, and it works as an R value reference if it occurs after a plain old data type or a user defined type for R value reference, but for a variable type t in a template ampersand will work as a universal reference, and there R values will bind with R value reference will bind with R values, and L value, and universal reference will bind with L values and R values. So, this is for just a plain definition, and this is for a template type definition, right. So, if I write int ampersand in a function, then this will bind as a R value reference, but when I write t ampersand in a template situation and then the template is invoked, then it will behave like a universal reference. Some more examples are given here from the standard library, like vector. If you do pushback ampersand, that is how it is defined. So, this is a L value reference, there is a overload which is an R value reference, whereas m plus back is a universal reference because it is templatized. Okay. So, let us with this knowledge, let us move on to the next big problem that R value reference solves. The first problem that it solved is that of move semantics, and we have learnt about it pretty well. The next problem, as it is known, is called the perfect forwarding problem. The perfect forwarding problem is arises when in a template function I want to call another function and pass the parameters. I have a template function and I want to call another function from that template function, passing the parameters that the template function has received. So, this is what is called the parameter forwarding. So, you received parameters and you are forwarding it to another function. Now, when you do this forwarding process, what you want is that the L value arguments should work as copies and R value arguments should work as move. This property should remain, so that the move semantics that we have created with so much of care can be carried forward to all kinds of function calls. So, let us see what does that mean. So, to illustrate that, we have one template function right here, which has two type parameter T1, T2, both of them are given universal references. That is the this is written as R value reference. So, in the template type deduction context, this will become universal reference. So, this function f wants to call a function g and a function h. To g it passes parameter p1, to h it passes parameter p2, right. This is what it wants to do. Now, for g and h we have written two overloads. For g we have written one overload which takes const int ampersand, which means it takes an L value parameter, and it has another overload where it takes a R value parameter, right. So, we want to check that when I forward this call from f to g using parameter p1, which of these functions should get called, right. This is what is done for a plain old data type built-in type int. Similarly, I have defined another arbitrary class data, and I have defined similar functions with one with L value parameter and another with R value parameter for this user defined type data, and I call this h. This is just to show that the behavior is same for the built-in type as well as for the user defined type. In terms of f, g is passed the parameter p2. Right? This is the scenario. Now, let us see if I try to create two variables I of int and d of data. D has a default constructor. So, that is what will get generated. We are not really bothered about what the values are, we are more bothered about the actual binding of the functions. So, if I do FID, that means that I am passing L value parameter as P1 as well as L value parameter as P2, because both an I and D are L values. I am passing L value arguments to both of them. So, I expect that P1 and P2 both will be received as L values and will be passed on as L values. So, if it is passed on as L values, then naturally for G this will should get called, for H this should get called. So, you can see the respective statements given here to understand which function has been called, and I correctly find that those functions have been called. But now say, suppose I keep the L value for the second parameter, but the first parameter I change to R value, and I could have done it by having a function which returns integer also, but I have used that simple technique that we have learned is you can take any L value and call std move on that, which converts strips of the L value reference and gives it the R value reference. So, this becomes an R value. So, this is an R value I am passing and this is an L value I am passing. So, P1 is L value R value, P2 is L value. So, I would have expected that while for H it is an L value. So, this function should get called, this function should get called, but for G this is a R value. So, I would have expected that for G this function should have been called, but no, this function does not get called. G also binds with the L value version of the function, and you can continue this combination, see if both for if you have R value reference in terms of the function H, that is the function using the UDT parameter, even then you get the similar result. If both are R values, then also you get the similar result. In short, what you find that irrespective of whether the parameter is actually an L value or an R value, in spite of the universal reference, it is passed always as an L value, right. So, the forwarding is not correct, the forwarding is not happening in the proper way. The L value R value ness of the parameter is getting lost. Why is this happening? Very simple. The reason it happens is when I get the parameter P1 or P2 here, P1 is a name. So, it is a named parameter. So, when I pass P1 here, irrespective of the fact that I had got P1 possibly as an L value, but the fact that it has a name, the compiler deduces that P1 is an L value. It forgets that it was an R value. So, it does not matter whether P1 was received as an L value or an R value, the sheer fact that it has a name will make it a L value, and therefore, the L value part will happen. So, that is why this solution of forwarding gets broken. It is like in the move semantics, it is very easy to fix that, and for that in the utility again you get another function which is known as std : forward, and you specify the type you want. What it does is it checks from the T1 by the template deduction, it checks what is the reference type, is it L value reference or an R value reference, and accordingly from this pure L value it either maintains the L value reference if it is received as an L value, but it makes it the R value reference if it is received as an R value. So, std forward actually is a pair of functions which converts an L value to an R value if required, or keeps an R value as an R value. Right? So, with that when we try, we see that the first case has no difference, but then the second case where the first parameter is an R value, we see that actually the R value version of the function G is getting called. Similarly, say if you take the last one, both of them are R values, and in both cases the R value version, R-value reference version of the functions are getting called, right. So, by using std : forward, we are able to preserve the R-value, L-value ness under the template type deduction and forward perfectly. That is the reason this is called a perfect forwarding solution or perfect forwarding to say. So, you can in summary you can get exactly the behavior that you had wanted. So, that is the basic solution of the forwarding problem. Like in move semantics, we could achieve the move semantics with the help of function std : move. Here we can get perfect forwarding by std : forward, right? Very simple solution. Now, this entire process is very type safe in the sense that when it does the forwarding, it not only forwards to the corresponding type, but it does the same if for any type that is convertible to the given type. So, if I have a type H that we have, and if we have any type U which is derived from H, we know that an object of type U can be passed in place of a parameter of type T in terms of reference, and the same thing is allowed here. So, if I define a derived data by specializing data, then and we use the object of the derived data and pass it exactly the same way, either by R value reference or by L value reference, the entire code will work exactly as fine. But in the contrary, if I have some other class which is not related to, which is not a specialization of data, then try to do this parameter, make an object and try to pass it as a parameter, it will fail as it is expected to fail, because it cannot bind to an unrelated class. So, that tells us that this mechanism of universal reference along with the std : forward is not only solving the perfect forwarding problem, but it is fully type safe solution, right. Now, in fact, you can also make sure that if you want that compatible types will not be forwarded, even that can be done at a compile time using a specific feature called static assert. I will talk about it in one of the later modules, where you can specify, this is a, do not try to understand the details of this entire thing, we will come to that when we do static assert, but the basic thing is you are trying to say that the type of T1, what is the type that you will allow. So, if I say that for type of T2 here I will allow only data, then when I try to pass a reference to a derived object in L value or R value, then this code will not compile, rather I will get a compilation error message that T2 must be of data. So, in this way you can also statically control what you want, whether you want the compatibility to extend or how much you want the compatibility to extend and so on. Okay. So, in the following I have given a number of examples based on perfect forwarding. This one, the first one is based on a little variant of the earlier example, where instead of using std : move to generate your R values, we have directly used constants or direct temporary objects here, and you can see how the code similarly behaves. I have given some functionality in the class D also. I would want you to read and run this and see that you actually get these outputs. First is without std : forward, in which case everything will be forwarded as L value, and in the second case with std : forward, where appropriate L value or R value forwarding will happen. There are two other examples, please go through them. One is a generic factory method. Here what I want is I want to write a factory kind of function which takes, say, create object function, which takes a type and a value and gives me an object of that type. So, it is kind of as if it is in the factory, and these all should be generic in nature. And in the next couple of slides, slowly this whole code has been developed, and I do not want to go through it in the presentation. I would want you to run and study and understand this. So, this is example 2, which spans over 4 versions and finally gives you a complete solution to see how perfect forwarding can be effectively used in terms of achieving really powerful compact generic code. The next example is about applying, we call it a apply functor, which takes a function and its arguments and applies the function on the arguments, properly distinguishing the L values and the R values. Again, the solution is developed in 2 steps. First, you just take the naive solution and it will not work, because everything will be forwarded as L value when the apply tries to take the function and pass the argument to it. But if you when you use std : forward on the parameter, you will be able to forward it in the proper way. So, please go through and prepare on this. The complete solution is finally given in this slide 24. Moving forward, what is this std : forward? It is a simple function in the utility component of the standard template library, which has this property that if it gets a L value reference, then it will give you an L value reference. If it gets an R value reference, it will give you an R value. Right? So, that is what we wanted. The implementation is pretty straightforward. It is templatized by the type. So, for L values, you will get T would be T ampersand. For R values, T will be simple T. And in both cases, we want a universal reference to be returned, because then under template deduction it will be R value or L value appropriately. What you do is something very, very simple. You just do the remove reference, which we had done earlier, take the type of that and make an L value, do the same thing, make it an R value. Right. So, you can see that the forward has 2 overload, one for an L value parameter, L value reference type, one for R value reference type. So, depending on the reference type it has actually got, which through template deduction you will be able to choose the right one, and then you cast it always to the universal reference and return that. So, with this, your std : forward also is a very simple code which will work always. Now, before I close, a couple of comments about finally move as an optimization of copy. It is not something which is different, but the task of move can be taken up by a copy when it is not possible to move. Right? That is the essence of the whole thing. So, if my resource class has only copy constructor and no move support, then even though I might ask the resource in the copy constructor of the class, you would remember these classes we had discussed earlier in module 50. So, I am trying to do std move and trying to move that, but since there is no move constructor, this will also use the copy constructor. Right? It will, that R value will automatically be converted to the L value and will be passed to the copy constructor of move, my resource. Whereas, if I have the move support added, that is, if I have given a move constructor, the similar passing the R value reference, R value type will give me actually a binding to the move constructor of the my resource class. Right? So, it is very flexible, that it is not something different that you need to do. You are doing the same, your intention is to move in both cases, but depending on the support given by the target class, if it has move, it will move. If it does not have move, it will seamlessly, without bothering you, fall back to the copy version. So, that way it makes it always sensible that you write the move versions as and when it is possible, or as and when you feel that well, move is will be beneficial than copying, right. So, you provide that support, and in terms of using the other classes, it will translate seamlessly, because you will be able to take that work with move if the move support is there. If it is not there, it will seamlessly fall back on the copy support, right. So, this is the basic principle of design that it should be. Of course, note that there are some classes where the copy operation have forcibly been blocked, so that they are called move only types, where you can only move, you cannot copy an object, they are only movable, not copyable. We will talk about these kind of classes and objects at a later point of time, but in general the types should support move when it is cheaper than copy. That is the general principle that we learn from this support. And just to realize that we have always been talking about move benefits in case of move constructor, move assignment operator, but move in place of copy is not limited to these two functions. You can, any function can have a move version if it is meaningful. For example, here I am trying to I have a class myList, which has a list ID and a vector of values, integer values given. So, I have a setter function, a function to set an ID. Given an ID, it will set an ID. I have a value setter also. Given a vector of values, it will set that vector. So, these codes are trivial, but what these codes will do? We have known always that these codes will copy either this ID string or this vector of values and so on. But we can also, if we want, we can also write move versions of that by simply changing the parameter of this function to a R value reference, non constant R value reference. So, you just overload that function, and instead of copying, here you write a move. So, what will happen if your set ID is being set with an R value, then that R value will not have to be copied, which it would in case these were not there, right. So, this is what can make any function which needs to move around data more efficient to work with the copy. Now, naturally compilers give you support in terms of constructors, destructors, copy constructors, etc., that you have missed out, that you have not written. Move constructor and move assignment operators are also special in that way, that compiler generates the move operations if you have not provided, but you are asking for it, right. But there are certain conditions under which this will be done. One is all data members of the class must be movable, only then the compiler will generate, otherwise if you write it will be there, otherwise it will not be there. The second condition is there should not be any user declared copy or move operation. A similar rule applies for copy free copy functions also, that if you define a copy constructor, then no free copy constructor will be provided. But here, no matter if you have any move operation defined or any copy operation defined, then this free move functions will not be available. Similarly, if you have a user declared destructor, the move operation will not be made freely available. You will have to write it if you need them, right. So, these are some of the rules of compiler generated version. So, here I have just shown some examples, that if you have a destructor, that is if you are doing a custom deletion, then you have to decide what kind of copying you will do, because the free move will not be available, right. Unfortunately, free copy is available, which is a bad thing. We will talk about that at a later point. Similarly, if you are doing custom moving, then you have to do custom copying also, because if you have provided for, say, this is a class widget 1, which has two parameters which are copyable and movable. So, you just have provided a constructor, no copy construction operation, no copy operations, no move operations. Compiler will give you both move and copy operations in terms of construction and assignment. But if you add in this widget 2, if you add a user declared copy constructor, then no implicit move operation will be provided, though implicit copy assignment operator will be provided. Right. So, the custom move, if you have custom move semantics, then you must have custom copy semantics. That is what it all relates to, and that is so default is you try to define the move semantics in every case, make advantage of compiler generated move constructor and assignment operator whenever it is possible, but keep this in mind that whenever possible moving is cheaper than doing copies, and that can give you great optimization in terms of your code. So, in summary, we have learnt how Rvalue references work as universal reference and how to solve the perfect forwarding problem, and what is the way to design with move as an optimization of the copy. Thank you very much for your attention. We will meet in the next module.